Okay, hi everyone, welcome back to another lecture of COP 3402. Today we have another two lectures combined into one, so it's going to be first version control, how to use Git to track changes to software over time, whether you're working alone or collaboratively, and then we're going to be looking at build automation, specifically how to use the make build system to automatically compile your C code. I think that TA Taiwo should be here today. I'm not sure if he's here yet. He said he had something he had to do beforehand. But when he arrives, I said he can introduce himself to you all. He'll be the one leading the labs this semester. So when he arrives, Taiwo can introduce himself and you can all get to know him. Okay, so before we begin today, any questions? Any questions about the course, about the homework? I see there were some messages waiting for me on web courses. I haven't checked them yet, so if you sent me a message, I'll get to it after this. Somehow the desk got raised again, which I'm very glad about. I can stand and type comfortably now. Okay, so if there's no questions, I want to first go over first homework. Not really much to go over here. Just log into UCF and take a screenshot. I can do that here. I mean, for me, I don't have to enter my password or anything. I've configured this where I don't have to type in a password. I recommend looking into doing the same for you. You'll use this tool called SSH Keygen. Not essential for the course, but I mean, it saves you a lot of time and effort having to type your password every time you log in. So I recommend looking into that. I think in the course website we have links to that somewhere and how to do that. You can just Google it as well. Homework 2. I hope this worked and that there was no problems with anyone accessing these files. I think I can just download this here, like so. Yeah, that worked. So the big idea here was to use the different commands we reviewed last class. I apologize if I went pretty rapidly towards the end. We were running out of time. We had to use the commands from last class to restructure the given file tree in this tarball into the one shown here. Or here. So this should be the given one, and this is what you have as the result. You can use makedir, touch, cp, whatever to create these files. We're looking at the tree structure, not that they're actually files themselves. So, I mean, makefile should have been a regular file technically. It doesn't really matter for this project, but a makefile is a regular file traditionally, not a directory. So. Can anyone guess what this directory structure is supposed to sort of mimic? What real-world project does this directory structure somewhat match the directory structure of? So it's the Linux kernel, actually. So as we'll learn throughout this course, and this is of course not really that close to it, but it's somewhat close to the names of the directories. A kernel is composed of drivers, or includes drivers, which each expose functionality for accessing different parts of your hardware programmatically. So that's what this drivers directory is here. If you ever want to contribute to the Linux kernel, contribute more code, maybe you find some kind of peripheral that you have that the Linux kernel does not support, you can actually add code to the Linux kernel. It's open source software. And the driver staging directory is a good place to start. So kernel maintainers are notoriously kind of rude. If you try to upload code changes, they're not always so welcoming of those changes. But if you want to have like the easiest place possible to upload code changes to say I got some code into Linux, driver staging is a good place to start. So I don't know, just a interesting tidbit about real-world development. Yeah?
Is it a convention that files begin with a capital letter and directories begin with a lowercase letter?
No, so that's just because for makefile specifically, there's two different kinds of conventions for naming makefiles. Well, there's three technically. Makefile with a lowercase m, makefile with a capital M, and then you can also have GNU makefile with capital GNU. Those are three different common ways you'll see makefiles named. Typically not GNU makefile, typically just makefile with capital M or lowercase m. It's up to the developer. Yeah. But traditionally, I mean, often you'll see directories just all have lowercase names. Most files. Programmers are lazy. As we saw last time, one of the virtues. Okay, so if there's no questions, I think we can begin with today's exciting lecture on version control. So again, version control is something you'll see in real-world development all the time. And I think if you, especially if you choose to take the software engineering course here, CEN I think 5021, I can't remember the name, the course number. It's a 5,000 level course. I'm not sure how many 5,000 level courses you're permitted to take as an undergraduate. I think you can only take one. But CEM, Software Engineering with Dr. Kevin Moran is fantastic. He's one of the newer faculty members here. He will show you how to use GitHub. So if you like learning Git, well, I guess whether or not you like it or not, you're going to be using GitHub most likely as a real-world developer once you graduate. And that classwork prepares you for using GitHub and working in teams to collaboratively modify and improve on software. There's another 5,000 level course that I'll recommend to you as well that Dr. Zilla teaches, but I'll recommend that later in the semester when it's more relevant. But for now, just know that this stuff on version control will be relevant throughout the rest of your life as a programmer, not just for this class. So any questions before we continue? Yeah?
Unrelated, but is the sign-up sheet, can you just like go up there and...
Wait until I open UCF here for all the students to take attendance. This is to avoid students taking the sign-up sheet, signing, and then just walking out. So I don't want that to happen. That happened sometimes last semester. And I just got my student perception of instruction ratings back, and some students were not pleased that I permitted that. So I'm going to prevent that this semester.
Oh, okay. I just showed up like a minute or two late, so I thought it was just something.
That's fine. I haven't uploaded we're going to be using UCF here today for attendance, but I'm going to wait till the midpoint between the lectures to do that.
Thank you.
Of course. Okay. So no questions? All right, so we'll proceed. So to explain how version control works, I want to use a bit of an analogy here. Imagine you have a bank account and your balance right now is $31. You're almost broke, at least on that account. You don't need to have a record of your total balance after every single transaction. It suffices to have a record of individual transactions which sum up to 31. So you can see here in this example, you made some money, you spent some money on gas. I wish gas was that cheap still. Some money on food, and then maybe your employer reimbursed you for some of your expenses. They didn't reimburse you for everything, I guess. So in the end, you can see the total adds up to 31. So with this log of changes to your account balance, you can actually keep track of your total balance at any time. We're going to use this analogy to describe how we can keep track of the state of our software that we're writing, our code. Instead of simple increments and decrements to a balance, however, we're going to be recording changes, additions, subtractions to different lines of code within our files. And that's the intuition behind projects like Git, tools like Git that we are going to be using in this course. So like I said, the intuition is, again, record each change, each version of software to a log, and then document the descriptions of those changes. We're also going to attach some metadata, some descriptions, some titles to each of these changes, the times in which they occurred, etc. Can anyone think of like a very simple way of maintaining changes to different versions of a software? What's like the simplest way you can think of?
Like numbers after file names.
Yeah, exactly. Numbers after file names. You could have like, I don't know, the first project's going to be called hello, so you could have hello.c or hello1.c, and then you make a change. Hello2.c, make another change. Hello3.c. Or if you want to be really extreme, copy the whole directory to make sure the entire project has its own state of changes. There are some developers out there who do this, who don't use Git. They actually just keep track of different versions of software manually over time. And they're not bad developers. They have reasons for doing this. But I encourage you to use Git. It makes this a lot easier. So in keeping in line with this idea of changes over time being all we need to create the final state of our software, I'm going to introduce a lower level tool, which we won't be using much for this course, but it will help explain how Git works. It is called diff. So I'm going to open my command line here. Open this on the left, these slides on the left, go to my desktop, everything's here, it's clean. I'll make a file called hello.c, and I'll create a main function here. Actually, what I'll do is just print hello world. Hello world. Includes .io.h because we're using the printf function call, or library call, I should say. All right. So we have hello.c. What we can do is use the copy command to copy hello.c to a new file. We're going to call this new hello.c. I can cat out the contents of this file and show you that it's the same as hello.c right now. What I'm going to do is modify new hello.c to, instead of saying hello world, we're going to say goodbye world. Goodbye cool world. And now I'll run diff on hello.c, a new hello.c. And we can see that the output tells us that there is an apparent difference in these two files, which sort of checks out. If I cat out the contents again, hello.c, new hello.c, you can see the two files side by side, and then diff, we can see the difference explicitly listed up for us. So one thing to note about diff is that it's actually not really looking at the column, the character changes. It really considers only line additions and subtractions. So to diff, this line, hello world, is really not present in the output. Instead, we have a new line added, goodbye world. But diff also can report to us the specific line and column number, so we know for us as humans exactly where this change occurred. So we can see it was at line 4, column 4 is where the first change occurred. And I think that's correct, though I'm not entirely certain why it says column 4, because this doesn't seem to be column 4 to me. So that's one thing that I will admit I'm not too clear about. I'd have to read the man pages more about diff to understand what that 4 really means, because it seems to me that this is not the case. Oops. There we go. Hello.c. Oh, I see why. Because the line itself started at column 4. I have 4 spaces. And again, diff just looks at the first part of the line that changed. So to diff, the entire line was changed, and it started at column 4. Yeah?
So diff is tracking strict uniqueness even of duplicated characters?
What do you mean duplicated characters? Like?
Printf is different than printf based on what your actions were.
Yeah, I believe that's the difference. Yeah. I don't know, I'm not the best about diff because we're not going to be using diff for a lot of this course. It's just for the sake of example of chaining changes to create a file state of software. Let me show that and maybe you'll see more about why this is important. So, okay. So if we use diff between a piece of software or program, hello.c, and then new hello.c, we have this output. We can actually write this output to a patch file, change.patch. And if I cat out the contents of this patch file, you can see it's just the exact changes that were made, the exact output of diff. So don't have to worry about the syntax. The idea is that we're redirecting the output to a file. And that file, change.patch, has the contents of our diff, the output of our diff. We can use another command, which is often coupled with diff, called patch. And patch will take in a input file. I have a typo here in the slides. It should be the name of the original file, hello.c. And then a patch file, so change.patch. I'll fix this typo later. Change.patch. And then what it will do, if we specify the -o flag, we can actually specify an output file to apply this patch to and where it should go. So I'll say patched hello.c. And so if I run this command, we're going to use our patch and apply it to hello.c to generate a new file, patched hello.c, which will have the patch, the difference listed here, applied to the hello.c file. So you can see it says patch and file. If I cat out the contents of patched hello, it has the goodbye world message, not hello world.
Can you do the inverse of that?
Yes, I can. Glad you asked. So we can run, actually, patched hello and hello.c, or I'm sorry, change.patch, with the -r flag to reverse. If we don't do this, patch will actually ask us if we meant to reverse. So I'll just pass the flag initially. And now it says patching file patched hello.c, and we cat out the file, contents of that file. It says hello world. So we can go forwards, we can go backwards. We can't go sideways. Yeah?
Where is it storing the reverse if we're patching it? How are we
So if you don't pass an output file with -o, it just overwrites the file. That's why I passed -o initially. So yeah, make sure to always use, either you can copy the file before you patch it, or you can just use the -o flag to create a new output file for your patched file. And this might seem, again, like a little archaic, like why do we need to use this? But again, some development circles still use patch files, and that's how they manage all their changes. Linux does this as well. They do it a bit more in a more sophisticated way. They use Git to generate their patch files, which we'll see more about Git soon. But they don't use GitHub. Famously, you have to upload all your patches to Linux maintainers via email. You have to use a command line interface for email. Email has to be formatted exactly correctly. And they will manually apply all your patch files to make sure they all work. So it's very rigorous. But still, the point still stands. Some developers still use patch files. They eschew fancy tools like GitHub. Okay, so I guess maybe we can already kind of see, with being able to apply a patch and go back and forth, we can already form a sort of linked list, sequential structure of these patches, where we have one version of software, a patch, another version of software, a patch, and then another version of software, and so on. And this is the intuition behind tools like Git, which under the hood, that's all they're really doing. They're just maintaining changes to files over time. So Git lets us track changes and updates and et cetera to a piece of software over time. I haven't read this book. I've read like little pieces of it, snippets of it. I want to read the whole book one day, but it's a long book. But I think it's free and it looks to be very useful, so I recommend checking this book out, maybe at least giving it a cursory glance, pro Git. So yeah, I think you can see here, yeah, it's all totally free, all online. So how does Git actually work? Let me create a directory here. Let me check. Okay, so the next thing is okay. I won't do this yet because the next thing we're going to be doing, we'll be demonstrating all these points. But I'll just go over with an overview here of what we're going to be doing and the example coming up. So in Git, there are, when you have a Git project, there are 4 different regions in which your code can be, sections we have here in the table. The first of these would be the working directory. This is not to be confused with the current working directory. This is specific to Git. This is the area in your repo in which files that have not yet been committed to the local repository's database lie. These are files for which no history of changes exists. So again, if we were saying that every time we have a patch, we have a new addition to this chain of history of changes to this file, projects or files in the working directory have no history applied to them yet. They're not added for version tracking with Git. We can put files into a staging area to where their stages are ready to be pushed, ready to be committed to the local database with certain commands, and then afterwards we can commit those changes. Please wait till the middle of the lecture to sign your name.
I'm sorry?
Wait until the middle of the lecture to sign your name until we get to the breakpoint. Yeah, thank you. So we go from the working directory to the staging area. From the staging area, we commit those changes to the local repository's database of changes. And from there, we can actually push those changes to a remote repository. And we'll see all this very shortly, commands and how you can do all this, an illustrated example. But the big idea is you can have changes committed to your local repository's history and then again pushed to the remote repository. And you can even pull those changes back into your local repository to work across multiple devices or across multiple team members. You're all pushing your changes to the same remote repo and then pulling them all to your own separate machines. You can even have multiple remotes if you wanted to push your changes to different servers, for instance. I don't know exactly why you want to do that. There's probably good reasons to. Okay. This image, this figure from the Pro Git book sort of illustrates this concept where we have the files in the working directory, we make some changes, they go into the staging area, and then we commit them. They're added to the .git directory, which is a hidden directory every Git project has. And then if you check out the project with a command that pulls it from the remote repository, for instance, you would have all those changes added to your working directory. Yeah.
Check out in the library sense?
Checkout, and then, well, there's a command called git checkout. So yeah, we'll see that. Well, you actually probably won't see that because we're not going to be using it for this course too much. But you can use git checkout to check out different branches of your history in Git. That's a little bit on this course. You'll see that more in system software. Or, sorry, software engineering. This is system software, yeah. Yeah.
Do we need to know the specifics and the syntax on how to use patch, or just understand that that's what Git is built on?
You don't need to use that. You do not need to know how to use patch. Just understand that that's under the hood what Git is doing. Git is really not doing that much more. It's doing a little bit more, actually, but it's not that much more. It's mostly just keeping track of history of changes over time. And do any of you know who made Git? So, yeah. Do you know?
Yep.
Can you share?
Git?
Yeah, who made Git?
I forgot his name. He has a long beard.
I don't think you're thinking of the correct person.
Yeah?
I don't think so. Do you know?
Isn't it Linus?
Yeah.
Oh.
Yeah, Linus
Then
Torvalds.
he moved the maintaining to another person though.
Uh,
He made it first after like 2 days and he moved to other
Sure,
person.
sure. But he was the one that created it, though. That was the
Oh,
question.
okay.
So, yeah. But thank you for correcting me on that one, I guess. I didn't know he gave the maintenance over to somebody else, but yeah. So Linus Torvalds made Git. He's the same guy who made Linux. That's why it's named such. I think he might have made Git and helped him make Linux. I'm not sure. But yeah. So all these things are sort of connected. Hopefully you're being able to see that. And again, like I mentioned, you can push your changes to one server, and then or one remote repository, and then have those changes pull to different computers, different machines. For all of you, what this means is that you can push your changes to the grading server, because we have a grading server for our projects. You can push your changes to the grading server, pull your changes to your laptop, and then you go home, you have your big PC where you play your video games or whatever. You can pull your changes onto that and then keep coding from there. Okay, so to give you some concrete commands on what you do to actually interact with these different parts of a Git project, if you wanted to change a file in the working directory, you would do that with your editor of choice, Vim, Emacs, VS Code, CLion, IntelliJ, whatever. Git add to stage a file, git commit to commit it to the local repository, and then git push to synchronize the changes. There's some more commands we'll see, but these are like the 4 key commands that you'll need for this semester. And then more about this other diagram of how all these operations change the state of the software. I'm not going to hover on this one for too long because I have another diagram that's interactive that I want to show you with the example, which is the VC exercise. So remember, we have 2 exercises in this course, 1 for each half of the semester. They have to be completed within 1 week. The VC exercise is the first exercise. They're not very difficult. This one should be pretty easy. I'm going to show you how to do it all right now. So just make sure to do this as soon as possible. I think it is published today. So I recommend beginning it as soon as you can. Especially since, and I'll check this right now to make sure it's published, especially since exercises, unlike projects, cannot be resubmitted until the end of the semester. So you can only resubmit exercises 2 days after they've been due. So make sure to get them done on time. And yeah, exercises open today and the Hello project. Both of these are pretty easy, The Hello project, you will be required to use Vim or Emacs. I know I don't require it for most of the course. I told you I wouldn't require it, but I unfortunately kind of lied. You do need to use it for Vim or Emacs, for the Hello project. I've used Vim or Emacs, but there's a specific reason why. You only have to write a Hello World program. It should be easy. You shouldn't have to struggle too much with that. Okay, so enough about that though. Let's actually get into the VC exercise example. I'll go to the actual website page for this. It's on the left, and I'll keep my code here on the right. And while we work on this, I'm going to be modifying this diagram here to explain how version control actually works. So, okay, so for this exercise, there's some setup instructions you'll want to follow. I'm going to skip these because my Git is already configured. I have my username already configured. My email is configured. We'll skip these steps. You'll have to do those yourself. What you'll want to do is create a directory for the VC project. Does anyone remember what the -p flag does for make dir? I showed it briefly last time.
It's like previous directory.
Yeah, or parents, make parents, yeah. And it also does not throw an error if the directory already exists. So I'm going to copy this command, paste it in here, and there's no error because there shouldn't be, the directory already exists. Or we have the -p flag, so it should not be an error. So I'm going to change the working directory into that directory I just created. And in here, we can start creating our Git project. So I'm going to skip all these validation steps. I recommend following them. You really should follow these steps as you do the projects yourself. And as you'll see at the end of each project, there is a self-check section follow the steps in the self-check, please. It will save you a lot of heartache later if you do that. Okay, so the first thing you have to do to create a Git repository, I'm in an empty repository here. You can see ls-a. All we have is dot and dot dot. To create a Git repository, you can run git init, and you can all follow along if you want to. You can complete the VC exercise alongside me right now if you are so inclined. So I'm going to run git init, and you'll see it says that initialized an empty Git repository in this directory. But if we run ls, you see there's nothing here still, apparently. So what gives? I thought we initialized the Git repository. Well, if we run ls-a, you can see that the .git directory was in fact created. And this is going to have, I think, a lot of content in it. Yeah. Even with a totally empty Git repo, there's already all this content. This is what's going to be used to store all of those changes that I talked about earlier. That chain of patches, basically, under the hood, is going to be stored in this .git repo. Yeah?
Does tree imply -a?
What do you mean? I don't think it does.
Just because the Git stuff isn't hidden when you run tree. So
Well, I pass the directory to tree.
Okay.
Now, if I run tree like this, it actually doesn't show Git. So yeah, that's why. Not because it was implying -a, but because I specifically passed the .git directory to the tree command. Okay, so we have the .git repo initialized. Yep. I'll show this command, git status. This is going to be a command you'll want to run semi-frequently. It will show you the, as it suggests, status of your Git repository. If you have any files that have not been pushed yet, any files that have been committed, have not been pulled, etc., git status will show you all of that. So to begin, we're going to create a file here, a README file, which traditionally README files contain instructions on how to set up and install your software and run it, along with prerequisites, anything else you might need to use your software. A README file should contain all of that. We're going to create a starter one here with this command. What this will do, let me show you this first by itself. The echo command, we didn't see it last time, will just print out whatever you pass to it to the terminal window. So echo VC project just prints out VC project. What I'm going to do, actually, before I continue, I'm going to set an environment variable in bash here. And what that will do is change my prompt to be just a $sign, so it's a lot smaller. So the PS1 variable, if you change it, it changes your prompt to whatever you assign it to. In this case, I assign it to a $sign with space, so that I have a lot more space to work with here on the command line for this example, just so you can all see what's going on. Okay, so again, echo VC project, prints out VC project. We're going to use this greater than sign, we'll see more of that later about what that exactly does, to redirect that output to a file called readme.md. And now if we cut out the contents of that file, oops, you can see it just has readme. VC project within the file. And you can see if I ls my directory, there's now a readme.md file here. So any questions so far? What have we done? I haven't done too much, but I want to make sure we're all on the same page. Yeah.
So that echo VC project with the greater sign, it just puts that into README?
Yeah. So we'll see more of this later. This is what's known as a redirect. So we're redirecting the output to a file instead of standard out, which is the terminal itself.
Would that be accomplished similarly if you just went vim into README and typed out VC project?
Yeah, I could, but it's slicker to do it like this. Yeah. Also, it's less error prone in the instructions for us to do it like this, because you can just copy and paste the command rather than us assuming that you hopefully typed it out correctly. All right. So now if we run git status, you'll see something different. It says that there are no commits, but there's also an untracked file. So an untracked file is one which lacks any version history associated with it yet. We haven't yet committed anything about its changes over time to our local repository of changes. So to fix this, we can use the git add command, readme.md. Before I do this, actually, what I want to do is go over to the diagram that I promised you. We have a file here. I'll draw this in, let's pick a color. I'll pick green. Should be nice. So our readme.md file is here. What we want to do is move it from the working directory to the staging area. The command to do that will be git add. So if I run git add on readme.md and then run git status, it says there are changes to be committed. That means these changes are in our staging area now. So readme.md has moved from there to right here. And there's even an instruction here, git rm -- cached to unstage. Just be aware as you're using Git that Git often gives you hints on what to do for common operations. So if you're stuck, if you want to unstage a file, you have some changes you actually didn't want to commit, just read the instructions carefully and you can undo those changes. Okay, so the next thing you want to do is actually commit this file to our local repository, to its actual version history. So what we can use for that is git commit. Now, there's a few different ways to use git commit. If we run it just by itself, it will bring us to a window here in our default editor, which you can set by setting the editor environment variable. I think for all of you, I'm not sure which editor will open by default. I have it configured to open Vim. You can look up how to configure this. For me, it opens Vim when I run git commit. And then you are prompted to enter a commit message. This should be a message that traditionally should be less than 50 characters long, I think 50. And when writing commit messages, you should use the imperative mood, which means when you're saying a command, basically. So what I'll say is commit or add readme.md. That's an example of a decent commit message. And then below, with at least one line of actual content between the title and the body, you can actually write a full description. So we could say add the readme file for initializing this project. And then if I save and quit this file, it makes the commit. And if I run git log to view my log of commits, I can see that this commit is added to the actual version history for this program. Now, what often happens, or sometimes often happens, is that you have a typo in your commit message and you want to fix it. The way to do that, so let me just actually do this over here. So we've added our readme.md to the local repository with git commit. Now, to fix typos in commit messages, you can use the amend flag on git commit. And what that will do is open your last commit up in your editor again and let you change the commit message and then reapply the commit. So I could say initialize or initial commit maybe and leave it like that. And that would be the same thing. And now you can see in my log that the commit message has been changed. A useful one to know because often I find myself making typos when writing commit messages and it's useful to just know how to fix that one commit. Okay, so now if I want to make a change to this file, let's say I open this readme file up, and I want to make VC capitalized, let's say. Now, I can run git add again to add that change. So git status. You'll see there is a change again. I can add it, git add readme. Oops. And instead of saying git commit and just pressing enter, I can actually pass the message on the command line, and I can just say make VC or just capitalize VC. I can make this commit on the command line with the message with the -m flag. I'm mentioning it because it's useful, but I will say it's bad practice to use the -m flag. Generally, it's better just to run git commit and then type out a full command because it encourages you to put more detail into your commit messages. When you're typing on the command line, that encourages you to write a very small, pithy message, which is not very useful. It's very good to write very small, compartmentalized commits so that you can more easily manage your changes over time, and if you happen to enter a bug, you can go back to the exact version of your program in which the bug was introduced and find that bug that way. It's much easier to fix bugs when you have very smaller commit messages. Also, it's easier for code review, because when you go to develop software as a career, you're going to be submitting code to senior developers at first, and they're going to be reviewing all of your code. And they're going to want to look at small commit messages to be able to easily check your code for bugs or bad practices or whatnot. If you send someone a huge commit file or a huge change with a bunch of different files being altered all in one commit, they're probably not going to read it. They're probably just going to skim it and say, looks good to me, or take it back and then make this into a bunch of smaller commits. So it's good practice to use a bunch of small commits rather than one large commit. Okay, so we finished talking about all the local changes you can make to files using Git. Let's go on to the remote. Before I go on to the remote files, any questions? Yeah?
What you were just talking about with senior developer culture, is that latter part where they tell you break it up in a bunch of little commits, is that standard, or are you going to meet people who have the reverse complex where it annoys them if you submit a bunch of little commits?
Most developers will not ask you to split something up. Well, most developers will not ask you to send them a large commit, large monolithic commit. Most will not do that. And in fact, many developers probably won't even ask you to split it up into smaller commits because they can't be bothered to even ask you that. They'll probably just either say this looks good to me or this is way too much. They'll probably just say it looks good to me, honestly. But you don't really want that. You want to get good review from more senior developers when you start working as a junior dev. So you want to submit a bunch of tinier commits so that way they can actually have time to thoroughly review it. So, yeah. Yeah. Okay, so now let's talk about adding remote repositories. So here in this diagram that I have, this local repository is connected to a remote repository. We haven't done that yet, actually, in the code here on the right in this repository. So we're going to do that now by using this command, git remote add. So we're going to be adding a remote repository to this repo. We're going to be naming that remote submission, so I'm going to change the name here to match. And for all of your projects, you're going to be calling your remote repository submission. Make sure you're going to call it submission because that's what we're going to be looking for when we use the grading scripts. Let me specify the path, the URL to that remote repository. So we have access to this tool called Gitolite, which enables us to have our own private hosted Git servers on one of UCF servers here. This is sort of like our own miniature GitHub, basically. So you can upload your own files to this, and that's how we are able to grade your projects using grading scripts. This $user variable will expand to your username. I'll run this command so we have the remote added, and I'll show you what this means. So $user for me is br095187. It'll be your username. We use that here in the URL to make sure that your URL is uniquely identified for you. So now that we've set the remote, we can actually view it with the remote-v flag. You can see we have some remotes here for fetching and pushing. Fetching is when you're pulling changes. We'll see that more later. And then pushing is when you're uploading changes. All right. So there's some common errors throughout this instruction guide here that you might encounter. If you do encounter an error, please look for the instructions to see if it's already listed on how to resolve it. If you don't see any instructions on how to resolve the error, you can email me or come to my office hours. I prefer the office hours. I can help you out. Now what we're going to do is push this change to the remote repository. We're going to use this command, git push setup stream submission master. So we're saying git push to the submission repository what's on our master branch. And actually you can see right now, if I do git status, it says we are on branch master. So we're not going to go into branching too much, actually at all, throughout this course, but you can have different branches for maintaining different versions of your software contemporaneously at the same time. But right now we're just on the master branch, which is the default branch. So with this command, we are going to be pushing the contents of our master branch to the submission. And with this -- setup stream flag, we're going to say that this is the default for where we're pushing our master branch's contents to. So in the future, if we run git push again without any arguments, just assume that we mean push the master branch to submission. Set this here, and you'll see that I get an error. And I was fully anticipating this error. I set it up beforehand so that I actually had this error, because I want to show you how to resolve this, because you might encounter this error yourself. The problem is that what we're trying to do here is push readme to the submission. And really be more like copying it to our remote repo submission. But the issue is that it says here, the remote contains work that you do not have locally. This is usually caused by another repository pushing to the same ref. If you want to integrate the remote changes, use git pull before pushing again. So again, git tells us how to solve the problem. We just have to read the yellow text. What this means is that when I tried to run git push, there was actually already another readme.md file here, and I'm putting it in, maybe I should put it in red because red is the opposite of green. There's already another readme.md file in this submission repo. So our push is not going to work. This is analogous to if you tried to tell your bank that you had $1 million and you just immediately applied that to your bank account. But that's not going to mesh with the version history they have in their own records. So what we need to do is integrate the remote repository's changes into our own repository before we proceed. And the way to do that is with git pull. Now you'll see there is, no other error here. You might get another warning when you run git pull on your end if you encounter an error, but Git will again provide you instructions on how to solve that problem. So again, just read the instructions carefully, you'll be able to fix the problem. Okay, and you'll see that Git also instructs me to use the setup stream flag for git branch. That's because our previous command git pushed failed, so our attempt to set the upstream to submission also failed because the git push command totally failed. But now that we've integrated these changes, you can see, let's see here, readme.md, well, I guess it's not that different. The changes must have been the same, or they just were skipped. I'll run the git push command as we saw before earlier. Master setup stream. Let's see. Git pull. What did I run wrong? Oh, I know what the problem is. I didn't specify the branch actually. So git pull. Remote is going to be submission. We're pulling into the master branch. So what git pull will do is take these changes that are in the remote and integrate them back into the local repository. So now our file should be like the one in the remote after I run git pull with the correct arguments. I didn't use the correct arguments before, accidentally. I didn't read the instructions. Here's the warning I was talking about. So there's different ways to resolve these changes when you pull a file that's in the remote into your local repository and you have different changes. I'm not going to explain what these different ways are. I recommend you look them up and read about them yourselves. They're not that complicated. I'm going to use this one. So I run this first, and then I run git pull again. And it says that there are some changes I'm going to have to resolve. So this is a bit more advanced than what I wanted to show, but basically we have to resolve these changes. I'm going to delete everything here, save that to resolve the changes, and this is more than I wanted to show, but sometimes you'll encounter this issue where you have merge conflicts. What I had to do there was resolve a conflict by choosing what parts of the file I wanted to actually keep when I go to push the changes. So I'll go back now to my git push command, and hopefully now it will actually work. No, I didn't stage the changes, that's why. Conflicts, git push, and I think now, let's see, git, yeah. Continue when I'm satisfied with my changes. So again, I'm just reading the commands that git instructs me to use right here. And I'll run git push, let's see if this works, and now it worked. So now I've actually pushed the contents of this readme.md file. I'll make this a different color to signify this. This is orange. I'm overriding what's in there with my file's contents here. Now if I run git status, you can see it's totally good. And if I run git log, you can see all the changes I made before to this repo have also been integrated into my local repository because I ran git pull. So all my other changes that I made in previous semesters I taught this course, you can see my last commit was in January. That was the time last semester when I was giving the same lecture. Those changes are now in my history as well. They've been integrated. So maybe that was a little confusing, I apologize, but I'm also kind of glad because we were able to fix it live and you kind of got an idea of how to solve these sort of annoying, sometimes frustrating changes or issues that can occur when you have errors in your tooling or unexpected issues in your tooling. Okay, so I think that's it. Last one I want to show, very last thing I want to show here. So I'm in the VC directory. I'm going to show you how to check that your projects are actually working correctly or that they were correctly pushed to Git, because I know for many of you it might be a little intimidating that you're pushing these changes to the ether and then you're hoping that you're going to be getting a good grade and you don't even know whether or not they're actually pushed correctly. The way you can check is to use git clone, which is right here. So the way git clone works is if you're creating a fresh copy of a remote repository, so fresh, one that doesn't already exist, you can use git clone. This is actually the wrong one. We're cloning from VC, I believe. Right here. Yep, this one. Yeah. You can use git clone to clone that remote repository into your local machine. And I'm going to clone this into a directory. So if you just press enter here, clone will actually try to create a directory of the same name as the ending of this path. So we'll try to create a VC directory. This won't work because VC already exists in my current directory. You can see right here, VC. The way to fix this is to just put a new name at the end of the command line here. So I'll just say VC test or VC self-check. And now if I run this, it will work. I have a new directory called VC self-check, and this should have the contents of my submission here. What we've effectively done is created a copy of this whole repository. I'll delete all this. And both copies of this repo are now linked to the remote submission, the remote repository called submission. Yeah. And if I cd into VC self-check, you can see I have my README file, which should have what is the same as this is what I had committed before from the previous repo. If I run git log, you can see there's my same history as before. So I recommend that you, when you're doing the exercises in this course, or the projects, make sure to always just cd out of your directory, run git pull or git clone, create a new copy of that directory, cd back into that new clone, and then run whatever tests that you want to run to make sure that it's working correctly. This will help ensure that we have on the grading server what you expect us to have. Because that's exactly what we're going to see. Whatever you get from git clone is what we're going to see, because we're just going to use git clone to get the contents of your repo. Okay, so any questions before I continue? Yeah?
I got confused when you had it on your local repository and then you went to push to the remote and you found a problem because they had the same file in the remote.
Mm-hmm.
And so you have to pull that file that's in the remote back to your local.
Yes.
And then when
I had to pull the changes, the history of that file. The changes that my remote didn't have, I had to pull those changes into my local commit history.
so it won't let you pull it if there's it won't let you push it if there's a difference.
Yes,
between
it won't. You have to make sure that you've resolved all those conflicts. That's the terminology they use.
And then that one you would have to just go into file and delete what's different.
Yeah, you have to go in, select what changes you want to keep, save it, add it, commit it, and then you'll have to run a special command, git something continue, depends on what kind of merge resolution strategy you choose, and then you can push it from there. You can Google all this. Now the thing is, that was more lower level than I hoped because you shouldn't encounter that as you're doing this project. I did that somewhat on purpose because I intentionally had a file in the remote to create that conflict to help show you what kind of errors you might encounter and how to resolve them. But if you're following the instructions carefully, you shouldn't encounter that issue when you're doing the project yourself. But you might encounter it at some point in your life as a developer. You probably will. Yeah?
I'm a little confused on that as well. Like, how is like README in the remote repository? Like,
Oh, I pushed that before. I had added that file there before.
oh, okay,
Yeah. Was that what you were going to ask? How is it already there?
yeah.
Yeah, sorry. I had already added that before, so that's why it was already there. Yeah. So I hope that wasn't too confusing. There was a little more than I had wanted to show. Okay, so I think we're still recording. It's good. What I'll do right now, I'll close that. I'm going to stop recording for right now. Okay, so again, recording, build automation. All right, so building software. How do we build a C project? What command do you typically use to build a C project? What program? GCC, right? The GNU compiler function. Does anybody use Clang, CLang? Yeah. Does anyone use the Intel compiler? Or the Visual Studio Code compiler? If you're on Windows, you're probably using that. Yeah. There's all these different C compilers. They all have slight differences. Yeah. GCC-O, hello.c. What if you have two C files? What do you do then? Sorry, maybe I shouldn't have shown the answer, but I think it's pretty intuitive. You just pass them both to GCC. What if you have 30,000? So again, I'm going to keep using the Linux kernel as an example throughout this lecture today, these two lectures. What if you have like 30,000 files? What should you do? Pass them all to GCC directly? Maybe that's a great idea. And there's smarter ways to do this. Let me see, is there something? All right, no, okay. So there's a smarter way to do this. You could use a command to find all the .c files across your whole directory hierarchy and then pipe them all to GCC and compile it all that way. And that sounds really cool, but it's really a bad idea. You don't want to have to pass all these files to GCC all at once. Yeah. So can we think of like some reasons? I kind of just went to the slide back, but can we think of some reasons why you don't want to do something like this and pass like 30,000 files to GCC all at once?
If you're like testing like a single file change, you don't want to have to build every single file in your project.
Okay, and why do you want to do that?
If you change too many things at once and everything crashes, then you're just going to spend a lot of time looking for everything wrong.
Okay, that's another potential idea. We don't know which file has the bug. We compile them all at once.
You don't need to recompile things that you haven't changed.
Yeah, you shouldn't have to recompile things you haven't changed. And why shouldn't we have to do that? What's it a waste of?
Waste of time.
Waste of time, a waste of memory. It's a waste of all sorts of resources to recompile every single file. And all we're doing is really we only need to recompile one individual file. Yeah.
I have a question on GCC. Is that just the same as like pressing run in VS Code?
Pressing run in VS Code?
Yeah.
Oh, okay. Yeah, I should bring this up. So if you use VS Code or code blocks or some other integrated development environment, some IDE, you might have a little button that says play. And what that button will do under the hood is run some sort of compiler. It depends on what operating system you're on, what the default compiler will be. And we'll compile your code to a binary for you and then run it. So when I say binary, I literally mean binary machine code that can be executed on your machine. That's what a compiler turns your C code into. We'll see more about this later in the second half of the course when we talk about compilers. But basically, what GCC and other compilers do is they turn code in a so-called high-level language like C into machine code, binary code that can be executed on your machine for your specific hardware. So the play button, I haven't used that, but I'm assuming that's what it does under the hood. So again, we don't want to pass all of our files to GCC every single time because it's a waste of our resources, a waste of time to wait for them to compile, a waste of time, a waste of memory to, by memory I mean RAM, to have our GCC storing all these files in memory and compiling them all at once. So this is where we introduce the idea of separate compilation. So I don't know, has anyone heard of the term separate compilation before? You have? Okay. So can you describe it? So I think maybe you know what it is intuitively. I think many of us have actually used this before. We just don't know it by this name. Separate compilation has been around as a concept for decades now. What it enables us to do is compile files into a project, the individual files of a project separately, and then link them together to form a final binary that we can actually execute. Now, I think I have some illustrations here. Yeah. So let me open up some code now. There's going to be quite a bit of coding in this lecture. So I'm going to remove everything that I have here. So all this is going to be gone. I'm going to use the asterisk special character, which expands to, it's a wildcard. It means everything in the current directory, essentially. So now if I do ls, you can see it's all gone. ls-a, yep, everything's gone. Nothing up my sleeve. So let's create two files. We're going to say main.c. Actually, we'll create three files. So in main.c, we'll just say printf the square of %d is %d. And we'll say square of x. I'll create a variable here called x and assign it to 3. Now, we're calling a function called square, which does not yet exist. So we're going to have to define a header and a C file eventually for defining that function. We'll just call it square.h. So I'm using quotes here for my include statement because I'm going to be including a file that's in my current working directory. This is different from the tags, the less than and greater than signs. That means you're including a file in your user include directory, your system-wide includes. So I'll be going to this file now, square.h. I can do that directly from within Vim by pressing in normal mode :e square.h. Now I'm editing a file called square.h. In here, I'll declare this function, square.h, as just a function which takes in an int. I'll call it x, and that's all it does. So this is the header. It contains the prototype of this function, the declaration of this function. It does not contain the definition of the function. The actual functionality is not defined here. We need this header, though, in order for the compiler to recognize that this square function has a return type of an int and an argument type of an int. So from here, we'll define the C file, square.c. And here, we will define our square function. And what we're going to do, we're just going to square the number given to us by multiplying it by itself. So return x times x. I don't strictly need to do this, but I'll do this anyway, include the header associated with this C file. Yeah?
So is this basically just like making a function where you call it in your main
Yes.
program?
Yes. So this is not something you really, like, this is not really anything exciting that I'm doing here. It's just, this is a really trivial example, very contrived. What I'm trying to do is demonstrate compiling multiple files together. So I just need to create some files that work together to show that. And that's what I'm doing here. So I'll quit my directory, quit my file now, right, quit my changes. You can see they all exist. And what we'll do is compile these files to form a binary now. We'll say gcc-o to specify the output file. We'll call it main. And we'll say main.c, square.c. And we have a type of an error here. I know another reason why. We're specifying two format specifiers, %d and %d, but we've only given printf one argument. So I'm just going to pass x here as the other argument. So the square of x is square of x. Now if I run this again, we get no errors. We can run that main file, and it says the square of 3 is 9, which I think is correct. Okay. Any questions so far? This is just sort of laying the foundation for what we're going to be doing for this lecture. Yeah?
You made a square.c, which is like the functionality.
Yes.
And square.h is pulling from square.c. But square.c has to include square.h. Like
So
two-way, it's not exactly like square.h is just pulling from square.c.
So your question is square.h pulling from square.c, and that's actually not correct. So square.h is not reliant on square.c at all. So if I count out the contents of square.c, you can see that, or square.h, sorry. Square.c is not mentioned in this file at all. Square.c mentions it, but strictly it doesn't have to. The only reason I'm doing this is because, well, the reason that I have to do this is because when we're compiling our main code here, our main file, main.c, we need some kind of declaration of the types that the square function accepts and returns. Remember, every function accepts values and returns values. In order for our C code to compile, we need to specify what the expected return type and argument types of the square function is for our compiler. And then for us to have the actual functionality of that function, the body, we need to define that function in square.c. And then when we go to compile these files together with our call to GCC, the functionality of square.c gets added to main.c and then form a binary. Yeah?
When we do this, instead of the play button sandbox of an IDE, do we take on responsibility for the fact that the compiled stuff is now sitting on our memory? Like, is that our problem if we let it happen enough, millions of times that we run, as opposed to whatever caretaking the IDE was doing for us?
What do you mean sitting on our memory? What do you mean? So you're saying there's something that we have to manage now that we're doing this ourselves. What exactly are you saying that we're having to manage?
Whatever sliver of our memory is taken up by the compiled program.
Well, it's only, no, so that's actually still going to be stored under the hood with your IDE anyway. You mean like the actual memory space used by the binary and storing it on your disk?
Yeah. the thing that we're avoiding by, compiling.
It's still there.
5,000
It's still there okay. That's not storage memory I was talking about. That was RAM memory. So
Right.
the memory in process. No, that still has to happen when you're pressing the play button because somehow the file has to get compiled.
Right, maybe I'm assuming too much. When an IDE does that, when the play button, I assume it's, eventually gonna garbage collect it for you. This is not that, so you have to do that yourself?
No. Talk with me afterwards about this. I'm not sure I understand your question still, but we can talk more about this afterwards. Yeah.
So when you run that GCC and you compile all of the files, and you're outputting the executable machine code to that main, and
Yes.
then you have to do the /main in order to run it?
Yes. Why can't I just use main? I think we talked about this briefly in the last lecture. Why can't I just run main to run a file in my current directory?
It's gonna try and pull it from your path.
Yes, exactly. So there's this path variable that I showed before. It's a sequence of directories delimited by colons, separated by colons. And what happens is when you try to run a program without specifying the path to the project, to the program you're trying to run, the shell, bash, will look in each of these directories separated by colons for a binary of the given name. So when I run main like this, it's going to look for a binary called main. It can't find a binary called main in any of these directories. So it tells me I can't find it. This is the name of the program. If you want to run a program from a specific location, you have to specify a path. And the current directory's path is always going to be stored in dot. So we do ./main to run the binary in the current directory. And now we can run that, and we see our expected output. Yeah.
And it's generally safe not to include like an extension for main, just because like I normally see like out used as an extension, but it's okay to not have one.
Yeah. Okay. On Linux, the default is to have no file name extension. On Windows, what's the common extension for an executable file? I think many of you have seen it before. .exe. Exactly. Yeah. And I'm not sure if Mac OS has an extension or not. I think it depends on what you're building. Okay, so this is cool, but we haven't really fixed the problem, right? We're still running GCC and passing all these files to GCC at once. So we're still compiling all the files together into one binary. And if I make a change to main.c, let's say I add a period here, for instance, I still have to compile both my files with this setup to change my binary. So we haven't really fixed the problem. One way to get closer to fixing this is to use the -c flag with GCC. C is short for compile only. We're not going to perform other steps of compilation, which we'll talk about later in the semester, but these other steps are going to be necessary to form an executable. What we're going to be doing with this GCC-C flag, if we pass it a file like main.c, you'll see we got no errors. But if we run ls, there's now a new file here, main.o. So O is an object file. We'll see more about object files later in this semester, but object files are essentially binary code that's not ready to be run yet. And the reason why we can't run main.o, because if I look at the main.c definition again, you'll see we are referencing this function square. But is square defined in main.c? Do you see the definition of square anywhere in this function, in this file? No, right? Square is not defined in this file. Square is defined in square.c. So this object file here, main.o, is also binary, but it lacks the definition of square, the square function. So the way we can give it that definition is to compile the square function as well from square.c. Now we have square.o and main.o as two separate object files here. And we can, what's called linking them, link them together to resolve the definitions of functions that main relies on. In this case, square. Now we'll talk about linking later in the semester again, but for now you can just think of it as like the intuitive sense of the verb link, to link two files together to form a final executable file. So the way you can do that is to just pass the name of the object files you want to combine to GCC. So we'll say main.o, square.o, and the out file will again be main. And now if I ls here, you can see the main binary still exists. It was overridden by that previous command. I can run it, and the output is the same as before. So GCC is intelligent. If you pass it object files, it will not actually run all the steps of compilation. It will only run the linking phase to link the files together to form an executable. And again, we're going to see more about linking and such later on in the semester. But for now, the idea is just that we're combining these files together to form an executable file, resolving the references to function definitions that they have between them. Yeah?
Later on, if you want to add, let's say, a new programmer file or .c to that, would you have to, could you just GCC, make another object file basically and connect it to that already combined one?
Yes, you could. Or no. Not to the binary main. You couldn't do that, unfortunately. But you could with, you could add it to this list of object files here, is what you can do.
Alright, so basically you have to pretty much name all the object files to make it into that one.
Yes. So this is a problem still existent in programming, is that linking is annoying, especially if you program in C++. This last step of linking files together to form an executable can take a long time, and people have famously complained about it. There's you can find lectures online, like long lectures, people complaining about link times for C++. It's kind of funny. Okay, but good question. So we sort of see the same idea here illustrated in the slides. I just wanted to preempt it and show you it firsthand so I could just explain it as I was going along. Compiling each file into its own object file and then linking them together to form a final executable binary. And then if we want to make changes now, so the beauty of this approach is that now if I make a change to main.c, let's say I want to delete the period now, I don't have to recompile source.c to source.o. I don't need to do that anymore. I didn't change, or I'm sorry, not source, square. My words mixed up here. Square.o. Yeah. I don't need to do this anymore because I didn't touch square.c, did I? I only touched main.c. So all I need to do now is recompile main.c to an object file. And I do need to relink main.o, the new main.o, with square.o to form main. But now you can see my change has been applied, and I didn't recompile the square.c file to an object file at all. So I saved that extra bit of compilation energy there. This is separate compilation. That's the idea of separate compilation. Yeah?
So just to clarify, essentially what you're doing here is you're taking all the files you have, you're compiling it into an object, and you're linking together those objects and storing it as binary code.
Yes.
And so now when you update one file, you just turn that file into the object and link that back to the executable you had before.
Yes, exactly. Relink all the files to form that executable again.
Okay.
Yeah. Good. Yeah. Good reiteration. Mm-hmm. Okay, any more questions before we continue? Because now I'm going to get to the real meat of this lecture, which is how we actually automate this whole thing. Okay, so this is cool, but we're still running all these commands manually, and that's really annoying. We should practice the virtues of a great programmer, which includes laziness, and not perform all these steps ourselves. Enter makefiles. So the way makefiles work is that they consist of rules. I'll create a makefile now to show you. I'm going to make this makefile with a lowercase m. You can use capital M if you are so inclined. You can even use GNU makefile if you really want to. I'm just going to use makefile. Now, the way make works is we're going to specify a target for each. So again, a sequence of rules. Each rule begins with a target. We're going to say that our target is main. And we have prerequisites, what main depends on. So we're going to say, in this case, main.c and square.c. And then in the body of main, this rule I should say, we're going to provide a recipe. So we have a target, prerequisites, and then in the body here, a recipe. Now in the recipe, we're going to write instructions, a shell command, which enables us to create our target from the prerequisites ideally. So we're going to say gcc-o main.c square.c. One thing to keep in mind is that in makefiles, recipes must begin with a tab. So you can see I'm pressing the left arrow, well, I'm pressing H, but the left arrow essentially to go back. I can't go back any further because I'm already at the beginning of this line. This is the tab character. And to show you this visually, I can set the list option in Vim to see whitespace characters. And you can see there is indeed a tab character right here. Oops, that was way too small. I'll turn that list option off now. Now what I can do when I split my screen here, so I have my screen open on the right-hand side here, my terminal emulator lets me do this. I can run make in my current directory. So it's my directory again, same as before, I just have that make file added now. If I run the command make will look in my current directory for a make file. Capital N, little m, GNU make file, they all work. And if it finds one, it will execute the first recipe, or first rule in the file to generate that rule's target. So the first rule in this file is this one, oops, right here. The rule's target is main, so make is going to try to create main based off the recipe in this first rule. And you'll see it does nothing. The reason for this is because it can see that main is up to date. So the way make really works, let me actually delete these prerequisites here to show you this. Let me delete the file main. This here. I'll delete the file main and then I'll run this again. So here make would actually create the file. If I try to run it again, it won't do anything. The reason why is because make is sophisticated enough, smart enough to know that if the file main already exists and the last modified timestamps of any files that main depends on are not more recent than when main was last created, then there it stands that there's no reason to recreate main, I should say. Because if none of main's dependencies have been changed, it should be the case that main should not change either. So we shouldn't need to waste resources recreating the main binary. Main can tell all this using just timestamps, basically. Now to show you how we can actually force make to remake a file here, we can go into main.c. I'll add that period back that I already removed earlier. And now if I run make will actually run the gcc command because it sees that one of the dependencies, in this case main.c, was changed. So therefore we need to recreate make to reflect those changes, recreate main to reflect those changes. So any questions so far? Yeah?
So this is just a macro?
It's not really a macro, it's a bit smarter than just a macro. A macro is a piece of code, a piece of text that you're replacing. Well, it's a named piece of text is what a macro usually is, or a named instruction, some named sequence that you're just executing. This is smarter than a macro because it can tell when a file needs to change based off of timestamps.
Okay.
Yeah.
What if instead of running that GCC, which would just recompile bulk.c files, we create bulk-o's and then combine them using the make file?
Yes. So you have preempted me on that. That is excellent. So that's exactly what we're going to do now. So you'll notice that this command here that I have shown you, this is like the first command we saw in this lecture, which is again not very efficient. We're recompiling all of our files into form one binary. So every time we run make, we're really just recompiling all these files from scratch to form the executable. And again, we're trying to avoid doing that. So we can actually, again, exploit separate compilation to avoid doing this. So we can create separate rules for each of these individual files. So I can say main.o depends on main.c. And in here, let me delete this actually. Here we can say gcc-c main.c. And now here we can change this to square. So if you're curious how I'm going so fast, it's just Vim key bindings. So I can view in a paragraph with VIP, Y to yank, P to paste, CW to change a word, get to here, press the period to repeat my last action, and again to repeat my last action. So This course is not about Vim, but I will be trying to persuade you to use Vim throughout the semester by just showing you some of these little fast things you can do with Vim. So now, there's one thing we have to change. We have to make our main file depend on main.o and square.o. And now, what you'll find, which is really cool about make, is that because main depends on object files, make will actually look if there's a rule to build these object files. And because we have rules to build them, make will actually recursively walk down the dependency tree to generate these files. To illustrate this, I actually have a diagram here. Main depends on main.o and square.o. Each of these files in turn depend on their .c counterparts. So if main detects that a change happened to main.o, it will just recompile main.c to main.o, and then use that to relink square.o with main.o to form main. So this looks like in practice. Oops. Yeah. Main.c had a change, so we only changed main.c, gcc-c, to create the .o file, and then we relink that with square.o to form the main binary. Yeah?
Does it require that the white space on lines 0 and 3 look like that?
0 and 3. 0 and 3.
What was 0 for a second? It was now 3 and 6.
Sorry, let me fix my charge my computer. So 3 and 6. No, you can use whatever white space you want. I just pressed tab because I wasn't thinking. I just pressed tab for. Yeah, you can use a white space here, regular space here. You only need tabs inside of rules themselves. Inside the recipes, you only need tabs. Let me plug in my computer so it doesn't die on us. Okay. So let's see, what else is from here? Because there's a lot of cool things I can show you now. Let's see what else we have. So we already saw this. Oh yeah, clean rules. So let's say I want to delete all my contents of my directory, or I want to delete the main binary and any object files that I've generated. I might want to do this if I'm packaging my file for distribution. Well, not distribution, but if I'm pushing my changes to source control, for instance, or I'm sharing my code with someone else, I don't want to give them my binaries because I assume that they're going to be able to run make to generate those binaries themselves. So instead, I just want to give them the source code. What I could do is manually run rm to delete these files, rm main, rm square.o, rm main.o, etc. But I'm not going to do that. Because we have make at our disposal, we can automate this process as well. So the convention is to create what's called a clean rule, which has no prerequisites. And what it will do is delete all the files that are generated by our build. So we'll delete main, we'll delete square.o, and we'll delete, we'll just say main.o back here as well. Go back, main.o. There we go. And now if I run make clean, main.o, square.o, you can see it deletes those files for me. Now there are two lingering issues with this rule. One is that we can't just run clean, make clean repetitively. We get an error, and we shouldn't get an error for deleting files that already are deleted. That should be silenced for us. So the way to do that, does anyone remember what flag we can use for RM to not throw an error, even in the case that the file does not exist? Dash what? R. Close. R is often used with F, but R is for recursive, to delete directories recursively. There's a different one. I think someone else said it. F. For force, yes. So dash F for force. Ignore errors. And if you're ever confused, if you're using Vim, I'm going to try and sell you on Vim again. You could say, oh, maybe I'll just type in man RM and to get the man pages for RM, but you don't have to do that. Because in Vim, if you hold Shift and press K on a word that has man pages, it opens the man pages for you immediately. So now I can search here for -F, and immediately we can see the -F option is listed in the options manual. And now if I were to run make clean, So I'll run that again. It runs the command without any issue. And there's one more pitfall with defining a rule like this, which is really more of a command rather than a target we're trying to generate. And that's that if I create a file called clean, we're going to have an issue. What do you think will happen if I try to run make clean now that I've created a file whose name is clean? Anyone guess?
It'll try to run the file first before it does the file.
Close. So it does something with the file first. What will it do? It'll check the file, and what will happen when it sees that the file exists?
Remove it.
Close. Not remove it.
It's gonna try and output everything.
Not everything. No. So remember, make. What happened when we saw that main had already existed? What did make do?
Check the prerequisites.
It checked the prerequisites, but it saw that main already existed. The prerequisites were all up to date. So what did main do?
Check the timestamp.
It checked the timestamp and saw that the timestamp was.
Change. Or
There were no changes. So main did what?
Nothing.
Nothing. So clean exists. So what is main going to do? Nothing. Clean is up to date. It does nothing. So the way around this, and this is specific to make, it's not like something special to software in general, or general to software, is to define a .phony target with prerequisites, which are named after rules. So we define a .phony target with a prerequisite called clean. This instructs make that the clean rule is actually not something we're trying to create. It's just the name of a command we want to add to our make file. And now you can see it runs the same as before, even though that clean file exists. And I'll delete that now. So we're going to give you make files for the projects. For most of the projects, we're going to give you a make file because this is how you build your code that we're giving you. Please do not try and write your own make files if we give you a make file because you might screw something up or it might just be incompatible with our grading scripts. Yeah?
Is there like a review tool to do that automatically or?
To create the make file automatically?
Yeah.
So there is a set of tools called auto tools. I don't know if that's what you're suggesting. I don't know if you've heard of that. But there's GNU auto tools, which is a more sophisticated build system that uses make as part of it. And it will basically generate and configure your project for your specific hardware, for your specific platform. Because if you might notice that the recipes here are all shell commands. This is specific to Linux. But auto tools lets you abstract away some of these commands so that it works regardless of your specific Linux distro, or I think it might even work for different operating systems as well. I'm not entirely sure. I don't use auto tools, I've just used make. But yeah. So it would automate some of that creation for you. You can also just create a template file and go from there. Okay, let's see what else we have here. All right, wildcard patterns. All right, now we're getting into the fun stuff, the really kind of crazy stuff. This stuff is not strictly necessary for you to know, but I recommend learning this because it makes you a better programmer in general. Using make, you can write your ideas more concisely. It also makes it easier to manage large, complex projects with these things I'm going to show you. All right, so first thing I want to show you is making this rule smaller, more concise. Make provides variables. It is technically a programming language. It is Turing complete. You can access these variables by prefixing them with a $sign. So if I have a variable up here, let's say I can say objects is equal to main.o square.o. And then I can say objects here, and this will actually expand to this list and make a list as any sequence of words separated by spaces, essentially. And now if I run make here, which by the way, you can do it directly from within Vim. Vim has built-in support for just running make, so I'll just run make like this. You can see it actually runs the file. It builds the file just as before. It builds the project just as before. I can even specify rules to run from within Vim as well. Make clean, and it runs make clean. Now, besides regular variables that we define ourselves, make also provides special variables, which we can access again with the $sign. $@ will expand to the name of the target of the current rule we are in the recipe of. So in this case, $@ is equal to main. So now if I run make again, we again get the same output as before. There's another special variable we can use, $circumflex. So I know what this character is called. It's called circumflex. You might call it a caret. I don't know, I'm a nerd, so I know it. So $circumflex, it will expand to all of the object files, all of the prerequisites of this rule. So now if I run make again, it still works. Let me run make clean first so we can actually delete this and then make. It still works as before. This $circumflex is just main.o, square.o. So any questions so far? So another cool thing you can do with make is you can define pattern rules. Static pattern rules are what they're called. Actually, first of all, I guess to motivate this, you can see there's some similarity, redundancy between these two rules, right? The only thing we're changing is the stem of the file, the name without the extension. In this case, main and then square is the only thing that's changing. But otherwise, these rules are identical. So make provides features for exploiting this across C projects. And make is like kind of built to have a lot of support for building C code. So one way we can do this is to swap out main.o with a %sign and %.c, or main.c with %sign as well. And then $circumflex, or in this case, I prefer to use less than. That specifies the first prerequisite. And what this will do is say, whenever we see a file that ends in .o, assume that it depends on a file of the same name that ends in .c, and compile that file using gcc-c, and whatever that prerequisite that we inferred was, the one file ending in .c, use that as the argument for gcc-c here. So again, make clean, make, you can see it still works just as before. And what's cool is that with this, we actually have like almost a template that we can just, copy and paste and use for all our C projects. So it may seem kind of like, oh, what's the point of all this? The point is you don't have to hard code anything pretty much. You can just copy and paste this template and it just works. We still have a little bit of hard coding going on here with the objects file, but we can change that too. Yeah?
So the thing that this automates is not, it doesn't automate updating the files themselves. It automates checking whether or not they need to be updated when you manually run it.
Yes, you have to run make. You have to run make. Okay. But there's ways to make that very fast, running make. For instance, to show you, I have a hotkey in Vim to run make for me. Because you saw I could run make within Vim. I can bind it to a hotkey, and then it just works. I can just immediately run make, and it actually will recompile my code. Yeah. So it is slower, but you were talking about the play button earlier. Let me see that here again. The play button, you have to press a button in VS Code to compile your code. I don't have to leave the keyboard. I can just press space M and then my key binding, and then it just recompiles the code as well. It's the same thing as the play button. And if you really want to get the play feature where you're actually running your code, you can actually add a rule, another phony rule here. I'll call it run. This is something I sometimes do when I'm writing C code. I'll say that it depends on main. What I'll do is just run main. And so now if I run make run, it will build main if it needs to build main, and then run main to print out the output. This is great for rapidly testing C code that has no arguments. If your program has arguments, you're going to have to change this a little bit. But if there's no arguments, you can write these rules and run them really fast and immediately test your code. I recommend writing rules kind of like this. Maybe you can have a test rule instead that tests your code, or the convention is to call it check. You'll see a lot of older projects, C projects online, they have a rule called check, and the convention is to run make check to run all the tests. So, yeah.
Would that one where you use the less sign? Would that only use main, and would that never use square?
This would use whatever the prerequisite is for this rule. So we're going to say, for instance, if this was main.o, main.c, this would expand to main.c.
So how does it know when to switch to the square?
Because it's a wildcard rule. It's a pattern rule. The % means whenever you have a .o file you need to make, then infer that the dependency is a corresponding .c file. So square also ends in .o, square.o, So if we want to build square.o, then we build it using square.c.
Oh, because it referenced the objects that was called in the main above it.
Because main, when we go to build main, it will see that square.o is one of the dependencies. Then we'll say, how do I build square.o? Oh, well, there's a pattern for building the .o files. We need the .c file. So it'll build the .c file using this recipe. Yeah. Yeah.
So does the percent like have to have a pair, or for example, instead of JS, you just have %.o?
You should have a pair with percent. Otherwise, it's unclear what the dependency even is.
Okay.
Yeah.
So then there's ways like expand it to the list.
You can do that actually. So this is a bit more advanced, but I will show you this now to show you the kind of the final piece of this puzzle of how you can totally create a generalized makefile. Instead of objects here, this is going to be a little weird. I'm going to bear with me. This is if it hasn't been confusing enough. This is when you asked. I'm going to show you, but this is a bit more confusing. So we can get a list of all the files in the current directory that end with a specific suffix by using this wildcard function here. This will say set the sources of this project, srcs sources.c files, to the result of this wildcard.c. And to test this, I'll just create a new rule here. We'll call it test. And I'll just echo the contents of sources to make sure this works. You can see it prints out main.c, square.c. So we got all the dependencies, all the .c files stored in sources, but we need the object files for main, right? There's a way to automatically replace the extensions of a list of files with a new extension. The way to do this is to say objects is equal to, and we would say sources colon %.c equals %.o. So we're saying in the sources list, match everything that starts, well, get the stem, and then cut off the .c extension, and replace it with that same stem, so the name of the file, main square, and replace that extension with .o. And now I can change this to echo out the contents of the objects array, so you can verify that this works as expected. And we can see main.o, square.o. I'll delete this test command, and now everything seems to be working. Main is up to date. I can run make clean just to verify again that this works. Seems to work correctly. And now, let's see here. I can just delete this as well, right? Main, I can change this out for not sources, that'd be bad. Objects. And now, does my makefile reference any specific file names? No, right? Main, but you can turn that into a variable as well, right? If I really wanted to. I'll just leave it as main for now. But main is not a file that it's a file that we create, not one that comes from the project. So now we have a template that can just work for every single C project that we have, basically. Yeah?
But if you had any like unrelated C files in that directory, it would also like include those as per.
It would. So this makes assumptions about your project. But there are some projects that use this structure. So I don't know if you've heard of the Lua programming language, but Lua actually has a flat directory structure for its C code. It's literally just a directory with just C code in it. That's pretty much all Lua is. So this would actually work for Lua. I mean, not great, but it would work. Yeah?
Just out of curiosity, if you wanted to like separate the object files and stuff and like file them like sort of in chunks.
Separate directories, or?
Yeah, like does the wildcard work, for example, if you like put them into directories or like?
You would need to specify, so you need a more complex build system here, and you need to specify the whole path to those files in different directories.
Okay, that's right.
The wild, yeah. You need to specify, so if you had sources in a source directory, you need to say source / that. And I'm not going to show you, you have to change the objects replacement as well, the pattern substitution here as well. I'm not going to show you all that, but it would be more complex. Yeah. So I hope this is somewhat clear. Yeah, variables, run tests, hello project. So I didn't go over this project. Let me show this really quick. Actually, before I do, one more thing I want to show you that's going to be pretty important for you writing code here. I'm going to make a Git repository here. Git init, Git status. You can see that I have untracked files, including these files that I generated using main. But it's bad practice to commit generated files to your Git repository. Because these are files that the user, in theory, they should be able to, create themselves by running the build system that you provide with your project. So the way to tell Git to not include certain files in your repository is to create a file called .gitignore. And in here, you can just specify, one per line, the name of the files that you would like to ignore with Git. I could say square.o, and now if I run git status, you can see those files are no longer going to be tracked by Git. So when you're writing your code for the projects, make sure to add, if there's not a .gitignore file already, make sure to ignore your binaries, your compile binaries or .o files. Ignore those in your .gitignore file, and that way you don't accidentally push a binary to the grading repo and have that graded instead of the source code that you actually pushed. So make sure to ignore binaries. Yeah?
Can you use the wildcard for that?
You can. I'm glad you asked. You could just say star.o, and that would be the same effect. That was your question? Yeah. So I'm glad that some of you are kind of seeing the pieces that come together, or I think many of you probably are. I don't think they're just the ones saying it. But I think, yeah, you can see how these pieces all sort of are connected and related to each other. Okay, any more questions? Yeah. The Hello project. I'll show this briefly. You have 2 weeks to do this. It's pretty simple. I didn't have time today to go over these steps of this, but I think if you follow the instructions, it'll be pretty simple how to do this. Basically, you're going to be using a command called script, which lets you record shell commands as you execute them and then play them back in real time. You can actually see your commands being typed out for you. It's kind of cool. We're going to be using that just to reperform these steps that you are going to be doing in this project to make sure that you correctly create a Hello World program using some command line editor like Vim or Emacs. If you don't like using them, you don't have to use them ever again after this assignment, but I think you should at least try them. Okay. Any other questions? Anything you want me to see or do since I have this directory here? Or any other questions before we go for until Wednesday? Yeah.
In the make file, do you need to use the wildcard keyword when you're using the wildcards?
If you're going to be getting the current contents of the directory, you need to use the wildcard. It's technically a function. You're calling this it's a built-in function for make. And the $sign again is to tell make, hey, we're going to be doing a make thing. So make specific thing. So yeah. Yeah.
Is there anything you need to study or prepare to be ready for that tomorrow?
No, just come with, you can come with questions, and if you haven't done the homework yet, just come, I mean, you probably should have done the homework, but yeah, if you have any questions, just come with questions, that's all.
Are you going to go over the Hello project next class, or are we just reading?
Next class, I should have time to go over it next class. Yeah. Start it on your own, but I should have time to go over it next class. Yeah. All right. Well, see you on Wednesday, then. If you have questions, you can come up and talk to me now.